The operating temperature of the metal hydride is determined by the plateau pressure thermodynamically and the overall reaction kinetics. On the other hand, the entropy term mostly corresponds to the change from molecular hydrogen gas to dissolved atomic hydrogen and is roughly constant for all hydrides. It must be noticed that calculating weight percent, both mass of hydrogen mH and mass of metal m, not only mass of metal, must be considered in the denominator. Where m hydride, mass of hydride equals m plus capacity, presentation in weight percent is very useful from technological point of view, because it gives direct information on how much of hydrogen can be stored in a material. Regardless of the units, there are several ways to express hydrogen capacity. The reversible capacity delta, mH/m hydride R, is conservatively defined as the plateau width, which can be considerably less than the maximum capacity d mH/m hydride max. In practice, depending on available pressure and temperature ranges, engineering capacity is usually between reversible and maximum capacity. Substituting P equals 1 bar, or 1 atmosphere, in Von Neut-Hoff equation can find a simple relationship between the equilibrium temperature, P plateau, required to give a mid-plateau pressure of 1 atmosphere H2, delta H and delta S. This equation is plotted for a number of hydrides. As can be seen, all the data points fit very well in a simple straight line, whose slope is equal to delta S minus 130 J mole minus 1 K minus 1. This clearly shows that the entropy term is indeed a nearly constant value for all the solid-state hydrogen systems. According to the figure, hydrides with formation/decomposition enthalpies of no more than 50 kilojoules mole minus 1 are required to achieve a low desorption temperature at 1 atmosphere of pressure. For instance, La-5 and T-Fe, which can desorb at room temperature, have delta H values of approximately 30 and 33.3 kilojoules mole minus 1, respectively. If the enthalpy term is too small, the T plateau at 1 atmosphere would need to be much lower than 0 degrees Celsius. Therefore, enthalpy term is considered one of the most critical factors characterizing any hydride from this perspective. A compilation of Von Neut-Hoff plots of several selected elemental, classical as well as complex hydrides is shown in this figure. The La-5H6.7 or Fe-T4 are examples of low-temperature hydrides, with high dissociation pressures above 1 atmosphere at room temperature. Thermodynamics can be used only to calculate the driving force for transformation, but it cannot say how fast a transformation will proceed.